So in the last class, we started with the discussion of pipe. Okay. So we saw a pipe is a half duplex pipe. Okay. So for creating the pipe, the parent should invoke the fork system call. Okay. After the fork system call, the pipe will be created. Okay. And through the pipe, the process. Okay. These are two processes. Parent and the child process can communicate or pass the data through the help of pipe. So every process, okay, will be having the two file descriptors, one for reading and another for writing. Okay. So this is what we have discussed. So coming to the next one, uh, next function is popen and pclose. Okay. So here these two functions, okay, performs all the task like creating the pipe, fork of a child, closing the unused pipes, okay, waiting for the command to terminate. Everything will be done by these two function. Okay, so here the process need not go for fork function and all. Okay, so this function itself will call the fork system call and it will create the pipe. Okay, that is the difference between our previous pipe function and this function. Okay, so here what happens? So here for creating the pipe, okay, the fork system call need to be executed. Okay, you have to execute this system call. The parent should execute this fork system call. After that, the pipe will be created. Okay, and every time you have to take uh, the responsibility of closing the descriptor once the task is done. Here you can see here we are closing the descriptors. Everything okay is done here. So, but here okay in the p open and p close. Okay, so you need not go for calling fork system call. You need not go for creating the pipe. Okay, so no need of like yeah, no need of terminating or closing the pipes. Everything is done by these two functions. So this is a prototype. Okay, so in the prototype they are having two parameters. One is a command string, another one is type. Okay, so this is to open the pipe and this one is to close the pipe. Okay, so here first function p open. So here it returns a file pointer. Okay, so if it is capable of creating a pipe, if everything is okay, okay, a file pointer will be created, and in the case of error, null will be returned. Okay, and similarly, p close function will uh, returns the termination status. Okay, the termination status of the pipe, or it returns -1 on error. Okay, you can see here description is given. The two functions takes care of creating the pipe, poking a child, okay, closing unused ends of the pipe, okay, executing a shell to run the commands, waiting for the command to terminate. Everything is taken care by these two functions. Okay. So here popen function shall execute the command specified by the string command. So here you have the first parameter, that is command string. Okay. So this command string, okay, here you are specifying some task. Okay. So that task will be executed. Okay. And it shall create the pipe between the calling program and the executed command and shall return a pointer to the okay, stream that can be used to either read from or write to the pipe. Okay. So here we have a syntax. Okay. So here you can see there is some command, okay, command, some task need to be done. Okay, and this is under the type is here, type value is R and here the type value is W. So that is the second parameter. Okay, so type value is R and here is W. So type R means, okay, the file pointer is connecting to the standard output of command string. Okay, you can see here, okay, there are two processes, one is parent, another one is child. Okay, so they are executing okay, certain commands. Here what happens is The file pointer, okay, file pointer, you can see here, this is a pointer where it is connected. The file pointer is connected to the standard output. Okay, it is connected to the standard output of the command string. Okay, so whereas if you go for the type W, the file pointer is connected to where it is connected to, okay, standard input, okay, of the command string. So this is for reading and this is for writing. Okay. So the next one is coprocess. So using this pointers, you can either read and you can perform the write operation. You can execute any commands. So the next topic is coprocesses. Okay. The Unix system filter is a program that reads from standard input and writes to the standard output. Okay. So here there are we saw different types of files, right? In the previous module we saw there are different types of files: standard input files, standard output files, standard error files. Okay. So here, okay, in the case of Unix, it makes use of standard input for, okay, for reading from standard input, and to give the output, to show the output or to write the output, it is making use of standard output. Okay. So these two files are used for performing read and write operation. You can see here, okay, standard input and standard output. So this is for reading and this is for writing. Okay. Filters are normally connected linearly in a shell pipes. Okay. So filter becomes a coprocess, okay, when the same program generates the filter's input and reads the filter's output. Okay. So here, the filter becomes so here the filter is what? Filter is a program that reads from the standard input and writes to the standard output. Okay, you can consider it as a filter that reads from the standard input, okay, and writes to the standard output. This is for reading and this is for writing. Okay. Now this filter becomes a coprocess when, okay, same program, okay, same program generates both input as well as output. Okay, usually what happens, uh, usually the input is given by some other program, okay, so that will be fetched and after that processing will take place and output will be given. But instead, okay, if the same program does both the things, okay, reading as well as writing, in that case we call it as a coprocess. Okay. Coprocess normally runs in the background from the shell, okay, and its standard input and standard output are connected to another program using pipe. Okay, so here they are background, okay, they are running in the background and they coprocess make use of a single pipe for taking input and showing the output. The process creates a two pipe, okay, one in the standard input of the coprocess and other in the standard output of the coprocess. So this is the example, okay, this is the example of deriving the coprocess by writing its standard input and reading its standard output. So this is example where uh, where we are showing the concept of a coprocess. Okay. So where it is making use of standard input and standard output, one for reading, another one for writing. Okay. So programmatic example is given here. So this is a simple filter to add two numbers. Okay. So this is example of coprocess where we are taking from the same program, we are taking the input, performing the process, and the same program gives the output to the standard input. Okay. So here, this is our terminal. Assume that this is our terminal. So this is a program of a coprocess for adding two numbers. Okay. So here we are making use of this one program makes use of both standard input as well as standard output file. Okay. And they are connected with the help of what? Using pipe. Okay. So there are two pipes, one for reading, another one for writing. Now in this example, okay, you can see here we are reading, okay, we are performing the reading, and we are using here scanf statement for reading two numbers. So we are making use of standard input file for reading two numbers. One is integer 1, another one is integer 2. Okay. Next we are printing, okay, we are making use of standard output file for printing the sum of two numbers. Okay, let us assume that we have passed 2 and 6. Okay, so 2 plus 6, it will give you 8. Okay, so that 8 will be the given to the standard output file. Okay. So here this example shows, okay, where we are performing both read as well as write in the same program. Okay, very simple example. So you can see here we are reading from the file and we are writing to the file. If there is any error, okay, display the error message. Next one is FIFO. So this is FIFO is the full form is first in first out. Okay. So this is an example for a pipe. So FIFO pipe, or it is also called as, okay, a named pipe. We can say it's a version of a pipe. Okay, a type of a pipe, that is FIFO pipe, or we call it as a named pipes. So FIFOs are sometimes called as named pipes, and pipes can be used only between the related process. So this is, okay, you can tell, okay, this is the one point you have to remember in the case of FIFO pipe. So this FIFO pipe can be used only between the related process. Okay, how it is related? Only if they are having the common ancestor. Okay, only if the common ancestor has created the pipe. Okay, if this is a pipe for transferring the data, this pipe should be created by the common ancestor. Okay, and then the related process can you make use of this pipe for transferring the data. Okay, this FIFO pipe make use of a prototype. Okay, this is a prototype or a syntax. Okay, so here the name we use as MK FIFO. Okay, make FIFO. So there are two parameters. One is path name, another one is mode. Okay. Path name for a FIFO exists in the file system, okay, where we are creating the pipe. So that path name we have to give, and mode argument. Okay, it is the same as the mode of your open function. Okay, read mode or write mode. Okay, so that mode you can use here. Okay, rewrite mode. So this is similar to the open function. Okay. So here read only blocks until some other process opens a FIFO for writing. So here we can perform two operations, read and write. Okay. So in the case of reading, read only blocks, okay, until some other process opens a FIFO for writing. Okay. So you cannot perform reading, okay, unless there is some data in the pipe. Okay, unless some process has opened the FIFO for writing. Okay, Only if the data is written here, only then you can perform the read. Until then, the read will be blocked. Okay. Only if the data is available, only then, okay, you can read. Otherwise, the read will be blocked. Okay. Then the write will be blocked. Okay. The open for write only blocks until some other process opens FIFO for reading. Okay. So this, okay, this write, okay, write only, okay, only if the process opens the FIFO for reading. Okay. If there is any process is ready for reading the data, only then this write only block will be open. Okay. So, but an open for write only returns 1, okay, on error, okay, or it returns, these are some error conditions, okay, error numbers. If no process has a FIFO open for reading, if no process is ready for reading, okay, then it returns the error message. Either it returns 1 or it returns the error status as ENXIO. So this is the error status indicating that there is no process in the FIFO ready for reading. Okay. There are two main use of this FIFO pipe. The first thing is FIFOs are used by the shell command to pass the data from one shell pipe to another without creating intermediate temporary file. Okay. So here using FIFO, okay, you can pass the data from one pipe shell to another without creating. So imagine that there are multiple pipes, FIFO files. Okay. So there are two FIFO files like this. Okay. You can pass the data from one FIFO file to another FIFO file without creating any intermediate file. Middle, you need not create any file. FIFOs are used in client-server applications. Okay. So imagine that this is a process, okay, which act as a server, and there are multiple process, okay, which is acting as a client. Okay. Now this process can give the data to its client by making use of this FIFO pipe. So FIFOs can be used for client server application to pass the data between the client and the server. So this client can request for the data, any client can request for the data, and the server can give the response by passing the data through this FIFO files. Okay, so they can be used for client server applications. Some examples, okay, as I already said, one example is for client server applications. So here there are two examples are given for FIFO or named pipes. Okay. First example is you can use FIFO to duplicate output streams. Okay. That is, FIFO can be used to duplicate an output stream in the series of shell commands. Okay, so when you are executing multiple shell commands like this pipe, okay, so when you are executing multiple commands, what happens? Yeah, I had shown you this, okay, execution of commands, ls, okay, then after that, okay, you can go for one more command like cat command, okay, so any command you can go, or you can go for wc command, okay, after that you can go for ls command. So there are pipes, okay, so this is a pipe, whatever the output is given as an input for the next command. So in between, what is there actually, in between these two commands, what is there? That is a pipe. Okay, so what you are doing, you are giving the output to this pipe, and pipe will pass that output to this next command as the input. Okay, so here in the series of command execution, this prevents writing the data to an intermediate disk file. So here what happens is, you need not see when you are executing two commands, okay, you need not store the output of this in a separate file. That is not necessary. Okay, so what you can do, you can send this output to a pipe. So pipe will act as an intermediate disk. Okay, they act as a temporary file. So another temporary file you did not create. Okay, so no intermediate disk file is required. You can pass output to the next command. So here you can see here. So make FIFO, you are creating a FIFO. Okay. And what you are doing here? Okay. So here, this is for what? Input, correct? This is redirection operations. Okay, that is less and greater than symbol. Okay. So here we are executing. You can see here procedure that processes a filtered input stream twice. Okay. So you are executing the program one. The output is given to two files. Okay. So you are taking some input. Okay. So you are taking some input. That input file is given as a input for this program one. After executing, we are giving the output for two files. One is program 3, another one is program 2. Okay. So this will show you okay how you can do this first task. Okay. Uh, this diagram shows the elaborated diagram using FIFO. So what it is doing is here okay, we are creating a FIFO. Okay, that FIFO is taken as an input for this program. So that is what given here. Okay, so you are creating a FIFO file for one. So this is a FIFO pipe you are creating. So that pipe is given as an input for this program 3. So that is shown in this diagram. So this FIFO pipe is given as an input for this program. So this FIFO file is used for storing some temporary data. Okay, what data we will see later. Okay, what type of data, from where it is getting the data, that we will show later. Okay, so here FIFO is a file which we have created. Okay, actual name is FIFO1. So that is a temporary, uh, okay, that is used for storing temporary data which is given as an input for the program 3. Next, you can see here, for the program 1, we are taking input from a file. What is that file? Input file. So that is this input file. So we are taking the input for the program 1 from some file. Okay, that is input file. So that is shown here. After that, okay, there is one more T-FIFO. So one more, so we are using T here to send its input to both. Okay, so this is a command. So this is a command we are using. So which is used to send its input to both FIFO as well as program 2. So what we are doing here, using this okay T command, we are sending whatever after processing. Okay, we are sending its output for both program 1 and for the FIFO file. So you can see here. So how we are doing? So from the program 1 directly using T command, one we are passing through the pipe, another one we are passing it to the program 2. Okay. So like this execution of the command takes place. Next one is, next application of FIFO is client server communication. Okay. So FIFO can be used for client server communications. So another use of FIFO is to send the data between the client and the server. Okay. If you have a server that is connected to numerous clients, each client can write its request to a well-known FIFO that the server creates. Okay, you can see here. So if we are having okay, one approach is you can create one single FIFO pipe and many clients. You can see a dot dot. So dot dot indicates that we have n number of clients. So n number of clients can write its request to single FIFO. Okay, so that request is given to the server. So server can perform some task and give the response back. Another way is you can create the separate FIFO pipe for each request. Okay, so each client can write its request. You can see here. Each client can write its request to its well-known FIFO. That who will create this? FIFO is created by the server. So this figure, okay. So first figure, that is left side figure, what you see shows this arrangement. Okay. Since there are multiple writers for the FIFO, so how many writers we have? Multiple clients are writing to this FIFO file. So request is sent by the client to the server. Okay. So that will be stored in a temporary pipe buffer, which we call it as a pipe. Okay, so this is the buffer we are using in the FIFO, that is pipe underscore buff. Okay, so this is the name of the buffer FIFO for storing the data in terms of bytes. Okay, so bytes is used. Uh, so problem in this left side approach is that, okay, problem in using FIFO for this type of clients or application is that how to send the replies back to the server, from the server to the client. How to send? Okay, so we have one FIFO file here. Okay, how to send the response? Okay, so even though you send the response, okay, from to which client it should send the response, whether to the first, second, or third. Okay, how to represent that? Okay, so one solution is for each client to send its process ID with the request. So when you are sending the request, okay, so what you have to give? You have to give the process ID. Okay, so process ID is a unique ID for each individual process. So each client will be giving unique process ID for the request. Okay, server then creates a unique FIFO. Okay, you can see here, server then creates unique FIFO for each client using the path name based on the client's process ID. So what is this? Based on the process ID, what it will be doing? It will be creating separate well-known FIFOs. Okay, client specific FIFOs. Okay. So that arrangement is shown here. So this is creating individual client FIFOs. So using this, you can send, okay, for each request based on the ID, it can find, okay, this request is coming from the particular ID. Okay. So these are the two well-known applications of FIFO. One is for executing multiple shell commands. Okay. Another one is for client-server communications. So the next topic is system versus inter-process communication, or simply we can call it as inter-process communication. Okay. So that is communication between the process. Okay. IPC stands for inter-process communication. For inter-process communication, there are different methods available. Okay. So we can make use of message queue. Okay, I'll write it in short. We can make use of message queue for communication between the process. We can make use of the concept of semaphores. Okay. So semaphores we can use. So this is one more technique for inter-process communication. And there is one more technique, that is shared memory. Okay. So these are the three techniques for inter-process communication which we are discussing in this chapter. Okay, so there are three techniques for inter-process communication. One is message queue, semaphores, and one more is shared memory. Okay, so before moving on to these three topics, message queue, semaphores, and shared memory, we have to understand few terms. Okay, so few terms like identifiers, keys, permission structures, okay, configuration limits. Okay, so these are the terms we have to understand. So the first one is, let's understand what is an identifier and what is a key. Okay, so each IPC structure, okay, either it can be either of the structure, okay, in the kernel is referenced by a non-negative integer that we call it as a identifier. So all these three make use of a unique non-negative integer that we call it as a identifier. Okay, so that we have to understand first. Okay, so this So this identifier can be used to send or fetch a message to or from a message queue, okay, or sending a message using semaphores, or sending or reading the data using shared memory. Okay. So here there are two types of identifiers. Okay, identifiers can be two types. One is internal name, another one is external name. Okay. So here in the IPC structure, there are few IPC objects. Okay. So IPC structure will be having several IPC objects which are used for inter-process communication. So each of these IPC objects will be having an internal name. Okay. So identifier is an internal name for an IPC object. So this IPC objects will be having a unique internal name. Then each of these IPC object also have a unique key. Okay. So this IPC object has internal name and a key. So this key is also called as a external name. Okay. So this key is created by using a data type. So this is a data type we use, that is a key underscore T. Okay, so this is a data type which is used for creating the key, which is a long integer which is defined inside the header file this bar types .h. Okay, so this is a header file we use for creating the key. And once a key is created, so this key is converted into an identifier by the kernel. Okay. So key will be converted into a unique identifier by the kernel. Okay. Then there are several ways for the client and server, okay, for communication. So first one is server can create, okay, for client communication between the client and the server. What are the steps to be followed? So first one, a server can create a new IPC structure. What is that? So for between the communication between the client process and the server process, okay, client process and the server process. Okay. A new IPC structure need to be created by specifying a key of type IPC private. Okay, and so this is a key to be created IPC private, and store the written identifier somewhere. Okay, so again this identifier should be stored somewhere. Okay, some file it can be used for storing this identifier for the client to obtain. Okay, so here the server need to create a special, okay, key that is called as IPC private key. So this key will be stored somewhere in the file. Okay, so this file can be used by multiple clients for communication. So many clients, okay, client process can make use of this key for communicating with this particular server. Okay, then here the disadvantage compared to the pipe here is, here we need, okay, so since we are telling that these keys are stored in the file, okay, we need file system operation. Okay, so we need file system operation, okay, to perform reading of the file. Okay, so we need to read this key from the file, and server also need to write this key to the file. So server to write the integer identifier to the file, and client to retrieve this identifier. So for all this operation, we are dealing with the file here, correct? We are reading the file, server is writing the key to the file, client is reading the key from the file. For all this, we need file system operation, that is, we need read operation. Okay, so that we have discussed, right? So that file operations, we need read file operation, write file operation, close file operation. All these file operations are required. Okay. Then IPC private key, okay, whatever the key that we have created by the server, okay, IPC private key is also used in the parent-child relationship. Okay, so this key can be used between the parent process and the child process, not only between the client and the server, they can also be used between the parent process and the child process. Okay, so this first point tells between the client process and the child process. Second point tells this key can also be used between the parent and the child process. Next, in the case of parent and child communication, okay, parent and child process communication, what happens is the parent creates the new IPC structure. Previously, what happened? Server is creating the new IPC structure. Here, who will be creating? Parent is creating the new IPC structure specifying the IPC private key. So here, this key is created by whom? That is created by the server. But here, who is creating this key? It is created by the parent. And the resulting identifier. So this key is converted into identifier by the kernel is then available to the child after the fork. So after parent process create the child using fork system call, okay, this key will be converted into identifier and this identifier can be used by the child process for communicating with the parent process. Child can pass the identifier to the new program as an argument to one of the exe function. Okay, the child process can pass this identifier to some other process. Okay, some other related process for the communicating between the child and the parent. So that is second step. So first one is between the client and the server. Second one is between the parent and the child. How the key is converted into identifier and how the communication can take place. Third point is a client and the server can agree. Okay. Third one is can agree on a key by defining a key in a common header. Okay. So what we can do is in the second one, okay, where we are storing the key. So key will be stored in some common header. Okay. So this common header can be accessed by both the client and the server. Okay. Only related client and the server can access this common header. Okay. So here the problem with this approach is that it is possible for the key to already associated with the IPC structure. So already whatever the key that you are storing here, okay, maybe used by previous inter-process communication. Maybe it is used for previous inter-process communication. So that you have to take care. Okay. Client and server can agree on the path name and the project ID and can call the function. This is one more function to convert these two values into a key. So what can happen? Fourth step is, okay, we are storing, okay, we are using a common path name and a common project ID, which can be accessed by both the client and the server. Okay, and these two values, path name and project ID, they can be used for, okay, and they can be converted into a key. So using these two, path name and project ID, you can generate the key. That is by using which function? So that is this function F T. Okay, so this is a function that is used for creating the key using this path name and project ID. Then this key can be used by the client and the server for communication. The only service provided by this function is generating the key from path name and the project ID. Okay, so this function can be used for generating the key using the path name and the project ID. And later this key will be converted into identifier by the kernel. Okay, and this identifier can be used by the client and the server. So these are the 2 points. Okay, you have to remember how the keys, what type of key we are using, okay, between the process. Okay, the process can be either a parent and the child, or it can be a server and the client, where the key will be stored. Okay, how the key is generated. Okay, what are the different ways of generating the keys? How, where and all you can store the key? Either it can be stored in a common header, or you can store it in the file. So there are different methods of generating the keys. So this is a function. Okay, this is a function with the name FTOK. Okay, this function, built-in function, is used for creating the key based on two things. One is path name, another one is project ID. Okay, the path argument must refer to the existing file, the existing path. Okay, and 8-bit ID can be used for generating the key. Okay, so key will be having the data type. So this is the data type key underscore. Okay, key. Next thing what you have to understand is permission structure. Okay, so that's the next point. So So in the IPC structure, okay, in the IPC structure, which is used for, which is a structure, IPC structure, okay, for inter-process communication, for communicating between two process, okay, two or more process. So we need to create the IPC structure. So IPC structure, first thing what you have understood is identifier. How the identifier is generated using key. This is done. So this is what we have studied. Okay, we studied in the previous slide. Next thing what you have to understand is permission structure. Okay, so this is the structure is defines the permissions and the owner. Okay, so here permission structure defines the permissions and the owner. Okay, so this is a structure we are using with the name IPC underscore PERM. So IPC permission. So this is a structure. You can see there are fields like user, effective user ID, then effective group ID, then creators effective user ID, creators group ID, access mode, okay, then sequence. So sequence are initialized when the IPC structure is created. Okay. Then we have slot usage sequence numbers. Then we have key. Okay. So these are the structures, members we have under this structure IPC permission. Next, we can see what are the different types of permissions and either the name of the permission or bit. Okay. So what type of permission? We can go for read permission, write permission, group read permission, group write permission, others read and others write permissions. Okay. So there are three different types of permission: user, group, and other permissions. Okay. So sometime, okay, especially in the case of semaphores, okay, for writing, okay, we use the term append. Okay, append is nothing but writing. So here in semaphores, inter-process communication, we are using the term append. So these are the permission, and this is the structure that is used uh, for inter-process communication permission. Okay. Next term what you have to understand is after permission, next term is configuration limit. Okay, what is configuration limit? All the three forms of inter-process communication, either it is a message queue, a semaphores, or the shared memory, has a built-in limit. Okay, how much data they can communicate. There is a limit between inter-process communication between two process or two more or between more than two process. Okay, there is a limit. Okay, limit between the inter-process communication. Either limit is in terms of data, how much amount of data can be communicated between. Okay, limit can be in terms of data, or it can be in terms of CPU time, how much CPU time the two process can use, or it can be in terms of memory, or it can be in terms of resources. Okay, how much resource, how much unit of resource the two process or the process can make use of. So all these limits, okay, to be specified, building limits that we may encounter. So that is the next term, configuration limits. And all these limits can be changed by reconfiguring the kernel. So you can also change these limits. Okay, how much amount of data, how much bytes of data. So you can tell that a process can make use of only 2 units, or 2 units of resources, or 4 units of resources. Okay. So these are the three terms you have to understand. The first one is identifier and keys. Next one is permission. Third one is configuration limits. Next thing is advantages and disadvantages. Okay. So fundamental problem in the inter-process communication is that the IPC structure, okay, as a system-wide and do not have a reference count. Okay, that is a problem with the IPC three types of inter-process communication. That is, they do not have a reference count. That means, what is that reference count? We can create a message queue. Okay, that means we are highlighting one term of inter-process communication. Message queue. What happens in the case of message queue? We can create a message queue. Okay, and place some messages in the queue and then terminate the queue. Okay, what happens between two process? Okay, one technique, that is message queue. There are three techniques. Okay, one technique is message queue. So this message queue can be used for communicating between the process. So what happens is, you can create this message queue, place the data on this queue and terminate the queue. Okay, message queue and its content will not be deleted. Okay, they remain in the system until specifically you read or deleted by the some process by using. Okay, you have to use this command for reading this message, or you have to execute this another function for deleting the message. Okay, so this process will keep the message. Okay, let us assume that it will keep the message hello. Okay, once this process keeps this message hello, okay, either some process should read this message, okay, or this process should have some command for deleting this message if it is not necessary. Okay, now if it is not deleted, okay, then what happens? This message will remain in the system. Okay, till you reboot the system. Till you reboot the system, this message will be there in the system. So that is the drawback of this IPC structure. Okay, whatever the data that you pass between the process should be, okay, you should execute the function for reading that data, or you should have some way of executing the function and deleting the function. If you keep that message as it is in the message queue, then it will remain in the message queue and it will become an overload for the message queue till you reboot the system. Okay, what happens in the case of pipe? Suppose if you are using not message queue, suppose if you are using pipe in between the process, what is the advantage or what is the disadvantage? In the case of pipe, suppose if you are using pipe, which is completely removed when the last process to reference it terminates. So what happens in the you are using? Okay, so what happens when all the process completes reading the process data? What happens? It will delete the data Okay, when the last process reference, it will terminate. Okay, when all the processes are done with the reading the pipe. Okay, when the last process finishes reading the pipe, all the data inside the pipe will be deleted. You have to close the pipe. That pipe will be automatically will be closed when the last process done with the reading the pipe. Okay, so that is a first problem in the case of inter-process communication. Another problem is that, okay, in the case of IPC structure, another problem with IPC is that these IPC structures are not known by names in the file system. So there is no specific name in the file system. That is, we cannot access them and modify this property with the function. Okay. So suppose if you are creating this message queue, okay, this message queue will not be having, you can create any number of message queue. Okay, assume that you have created around 30 message queue. Okay, this message queue will not be having specific 30 names. They will not be having any names in the file system. Now you cannot modify this message queue using this functions. Okay, almost a dozen a new function system calls like this, okay, were added to the kernel to perform this inter-process communication objects. Okay, we can't see the IPC objects with the ls command like files. Okay, what happens in the ls command? You can see all the files, right? All the directories and all the files you can see using ls command. But when you execute ls command, you cannot see this message queues and all. Okay, so since you cannot see this message queue, you can't remove them by running rm command. You cannot see the message queue. You cannot perform any task on the message queue unless, okay, there are some special functions. Okay, these functions you must know. Only then you can perform some operation on this message queue. Okay, we can't change their permission with the ch mode. So ch mode cannot be used like file. Okay, like file, you cannot use your ch mode for changing the permissions. Okay, instead, for changing the permission, we need two commands. Okay, so these two commands we should execute for changing the permissions. Okay. So altogether, the second point what it is telling is, okay, it is not as easy to perform the task like a file. Okay, like a file, you cannot execute ls command, you cannot execute rm command, or you cannot execute chmod command for listing or removing or changing the permission. They have their own specific functions for performing any modifications. And third point is, since these forms of IPC don't have file descriptors, we cannot use multiplexed input-output functions. Okay, so here, so for any file operations, okay, we need these two commands. Select and poll command should be used for performing the operations with the message queue. Okay, so these are the three disadvantages of inter-process communications. Okay. Remaining, so today we discussed about the coprocess, okay, about Popen and pclose functions, about the FIFO pipe. Okay, then we started discussing about inter-process communication. There we discussed about three important terms: identifier, keys, permission, and limits, and what are the disadvantages of inter-process communication. Okay. Thank you. To answer your attendance, Naresh,
Present, ma'am.
Navina,
Yes, ma'am.